I'm Barnaby, I'm the team lead of Strathsets, and I'll be taking you through the preliminary design review for the Mach-25 competition for our entry Stratosphere 4. So to start with, our primary mission is to launch our 1 kilogram payload to 2 kilometers on less than an L-class motor, and second, also to deploy a payload at apogee that descends under a permanent recovery device. Our secondary mission is to use AI to analyze land usage and classify it as urban or rural. Also, to use AI to compress and upscale video for transmission. And finally, our tertiary mission is to count this flight as a certification flight for our Firefly flight computer by comparing the data from it with our COTS computers, as well as to test the user experience of Firefly in a high-pressure environment. Here's a quick table of our team structure, with myself as a team lead and Daniel as our vice captain. Daniel's also the electrical lead. We also have Jamie and Alice as our mechanical leads, and Kyle as our coding lead. I'll pass you over to Daniel to go through a ConOps of our mission.
Moving on to the concept of operations, from integration to recovery. We've had large issues in previous years in this area of integration, so we've taken key steps to improve our processes for procedures, design, and testing to ensure we have a successful launch. What I'm proud to present is a high-level overview. Each of these steps will be thoroughly planned, procedures written, and practiced well before launch day. The first phase is pre-integration, where we prepare our recovery systems, we do our final computer configurations, battery checks, and seal both the CANSAT and avionics bay. Next is our integration phase. We do our final AV bay checks, we assemble the aft with the main parachute, put the AV bay on, and then our forward with the CANSAT and chute, our drogue parachute, and an ejection piston to ensure successful deployment, and then our AV black powder preparation. Next is motor integration. At this point, the rocket is ready to fly. Which brings us to launch preparation, where we attach our flyby rail guides, put on the rail, and upright it, activate our flight computers, and do our final continuity and telemetry checks, inserting niter, attach the launch box, and we're ready to launch. This is our ConOps for flight. So just before flight, we've armed our computers. Our telemetry is going. The CANSAT will be in a low power mode, where it's not sending video, where we will send a high power command to engage that, so it starts drawing more power, and we'll be sending video from here onwards. At t equals 0, you'll have motor ignition, with burnout just a few seconds later. We'll reach our apogee of 1900 meters at about 20 seconds, with drogue deployment happening very soon after that, and our backup happening 1 second after the main. The CANSAT deployment will happen at apogee, with it reaching its downward-facing AI data phase immediately afterwards. At 70 seconds, we'll have our main deployment, with our backup triggered at 300 meters and our main primary deploying at 1,000 feet. So we will also have our vehicle landing 90 seconds later, and we'll lose our signal for the vehicle, and then a couple minutes later, our CANSAT will land. We'll lose the signal there. Now we enter a recovery phase. We've got backup tracking from multiple sources on both the vehicle and CANSAT, so we expect this to take less than 4 hours this time, and then we can start our data analysis, prepare for a post-flight review.
So here's a diagram of Stratosphere 4. We'll be ejecting our payload and our drogue chute from the forward bay here, with ejection charges on the forward and aft side of the avionics bay. We'll also be using a flyaway railguide system. We'll go into more detail on that later, as well as 3 centering rings for our K1440 Pro 54 motor. In deciding the separation points for our vehicle, we've learned from our mistakes last year and moved the separation points a bit further away from the ejection charges. So hopefully the components can gain a bit of speed before leaving the vehicle. I'll pass you on to the mechanical team to go through the rest of the design concept.
This is the nose cone. The main section is a fiberglass layer created using a 3D printed mold. There is a 3D printed PLA tip, which is screwed and epoxied on. The fiberglass section connects non-permanently to the bulkhead section using bolts which thread into threaded inserts set in a 3D printed bracket. The bracket is epoxied into the fiberglass section of the nose. The bulkhead section consists of a phenolic tube which inserts into the airframe of the rocket, and the bulkhead itself is a water jet cut piece of fiberglass which is epoxied to the inside of the phenolic tube. The bulkhead contains an eye bolt which is threaded and epoxied in, which connects to the shot cord, tethering the nose to the rest of the rocket.
This is the AV bay. This will house our electronics and other things during flight. In this you can see where we have put the Easy Mini and the Quark, as well as our own computer, Firefly. That will be controlling some LEDs, which will be seen by the camera in this housing here. This housing is used basically with a battery bay cover to hold it in, so ideally we will not need extra screws. This will require a lot of testing. As well as that, we have our backup trackers, a drawer for a short-range tracker, either an AirTag or equivalent, as well as a slot for the Sino-track, which we are planning on using. That'll need a fastener as well, however, that has not been made yet. Here, you can see our remove before flights. More will be talked about those later. And here is the space for the 18-350s and the 18-650s. Those will be connected inside the AV bay instead of requiring a separate battery bay. One of the interesting things that we will need to do is we found last year when we attached the sort of permanent wire to connect the pyro through the outermost bulkhead, we found it was incredibly annoying to take on and off. And so this year we've decided to attach it to the inner, but seal it still with O-rings and foam in the center. Here you can see how that would connect to our computers. It is all going to be held together with threaded rods, which are M6 threaded rods. There are also, the computers will be mounted with M3 threaded inserts, which will be melted into the PLA Plus that we are using to 3D print this. Here are the requirements that we have already achieved and are working to achieve. This is the mechanical aspect of the remove before flights that we have been designing for Mach and for future projects. They will use a photo interrupter and a spring ball quick release pin that we have found online. That will spring in and then come out, and so that will hopefully hold them in place up until they are needed to be removed. There are threaded inserts which will connect it to the whatever piece of plastic we use, as well as TPU washers will be necessary to go in between the board and the plastic sled.
Now moving on to our launch vehicle open rocket as well as our motor selection. This is our diagram of our open rocket model for Stratosphere 4. Our current open rocket sims estimate that 2 kilometers apogee is very feasibly reachable, and we're reaching 1.9 kilometers with an extra 1 kilogram of mass margin applied to account for things like glue, things like paint, general uncertainties with the structure, as well as ballast that we might need during construction in order to get the static margin range correct. More details about the open rocket flight, total movement trajectory over time, and the stability margins are included at the end of this document in the appendix for easier viewing. Now on to the motor selection. We chose to use previous year's project's motor for Stratosphere 3 for this project, as we did not use it in last year's project. This motor is a Cicerone Pro 54 K-class motor it is a White Thunder propellant with this specification. The 17A is less relevant now though, as the motor has been plugged it was plugged during the Mach-25 launch competition, as we're using flight computers to control our ejection. This motor is driving the design of the rocket now because it was chosen from the start, as opposed to the other way around being the case where the rocket would typically drive the motor that would be chosen.
So for a brief overview of the deployment events that will occur during the flight, the first one will be the flyaway railguides at about half a second after ignition. These will be made of a 3D printed plastic for these rings, as well as either a fiberglass or a carbon rod to hold them together. We do have successful flight heritage with a flyaway railguide system, but on a much smaller vehicle at NRC 2024. This system will be based off that one, scaled up in terms of diameter as well as the strength of the springs. Our second deployment event will be our ejection piston and camsat at apogee. Our ejection piston is made of a hand-laid-up fiberglass once again, with the shock cord going through the center. The camsat will be discussed further on the next slide with Jamie. Finally, our parachutes will have an 18-inch parachute for our drogue, so for a descent speed of about 35 meters per second in the first 2/3 of descent. And at either 1,000 feet or 300 meters, as our backup, we'll deploy our main parachute, which is a 48-inch chute to descend at about 11 meters per second. And finally, our camsat, we're targeting a touchdown speed of about 10 meters per second, but we've not selected a parachute for that yet. As I said, I'll pass on to Jamie to talk about the camsat a bit further.
I will now take you through the design of the camsat. At this current moment in time, the CANSAT does not have a very defined 3D model. However, the points I would like to highlight are that during ascent, the CANSAT will be stowed vertically with a camera pointing directly outside to capture video of the ascent. And then due to the CANSAT parachute being attached to either end, it will rotate to allow for the camera to be pointing directly downwards and allow the integration of the AI part of our missions. The CANSAT will be comprised of PLA Plus, 3D printed, along with the internals to allow for the mounting of the computers, and it will have fiberglass bulkheads. There will also be threaded rods going through to provide structural stability.
So in terms of manufacture, there are 3 major processes we'll go through for manufacturing parts. The first one will be a hand layup of composites. This will be saved for the nose cone and the ejection piston. Secondly, we'll be 3D printing some components, including the tip of the nose cone, the sled for the avionics bay, as well as for the CANSAT, and the internal structure for the CANSAT as well. Finally, we'll be using a water jet cutter on some GFRP sheets. These will be for our fins, centering rings, bulkheads for the rocket, and as well as bulkheads for the CANSAT. I'll pass you on to the electrical team, who will talk more about our Firefly system.
Moving on to Firefly Ultra. This is our latest line of flight computers. It's got advanced IMUs, radios, got a GPS pressure sensor, the works, and dual pyro. These will not be in control of actual live pyro on this flight. They'll be controlling LEDs for certification purposes. As we are currently going through the UCRA certification process for this computer, we don't anticipate that to be finished by Mach, so this will be proved as a test flight, not an actual flight with this in control. Also in the rocket, we'll have the video board in the CANSAT. This has multiple LoRa radios and a PyCompute Module 5 to do both the live video streaming and AI video processing. On the ground, we're developing our Ultra ground station, which has multiple radios for frequency division multiplexing and display to show our telemetry in easy-to-read format when we're recovering the rocket.
So we were planning to do 2 AI features. First off was AI land use classification. So we were exploring the literature and looking at various different model architectures. What looks the most promising so far is the UNet, which seems to perform very well in literature, and it seemingly is very easy to train, so we're likely to go for that. For our AI video compression, we're planning on using frame generation via diffusion models. So sort of the idea is that the rocket only sends a few frames down to the ground, and additional frames are generated in between. And once the error rate gets high enough, we send over new frame data. So using this technique, you're able to get bit rates as low as 0.02 bits per pixel, which is about 5 kilobytes for a frame.
Moving on to telemetry. We've got multiple telemetry sources on both the rocket and the CANSAT. The first is a Firefly Ultra in the avionics bay. They'll be transmitting on 868 or 869 megahertz, depending on what is most used on the day, and that is IR 2030 compliant. We'll also be using a Sinotrack 2G GPS tracker, which is a cellular GPS tracker, and an AirTrack for short-range identification. Next, we have the CANSAT, which will have a Firefly Ultra, again 868, 869, based on availability, and a video board, which will be in the 2.4 gigahertz ISM band, again IR 2030 compliant, and another Sinotrack cellular GPS tracker, and an AirTag for short-range identification. Finally, on the ground, we have our ground stations. The Ultra ground station, which has multiple 868, 869 radios, so we can receive all of this telemetry at the same time, at the same place, and the tracking ground station, which is both the 868 radio for receiving position information from the CANSAT to align its antenna for the high rate 2.4 gigahertz data stream. That will then go to a laptop for monitoring and be streamed on our Twitch stream to the internet.
Here we have a table of our project risks. This remains mostly unchanged since the initial outline design. Feel free to pause the video or look at the PowerPoint to look in a bit further detail at the table.
Our overall budget for this project is £4,340 approximately. We also have broken this down into our main categories. The biggest one of these is our entry fees, which will be about, we estimate, £1,500. And then as well our accommodation and then Firefly Ultra are our biggest 3 expenses. Our funding for Firefly Ultra will be coming from various places as well as our MAC budget, as we are currently working on a certification campaign, and so we will be funding it from various places. The Other categories we have are our mechanical costs, such as our hardware and fittings and the airframe, as well as the video streaming and flight computer, as well as our launch box. We were awarded £3,500, which is approximately 80% of our budget, from the Strathclyde University Alumni Fund. We were also awarded £500 worth of products from the RS Student Fund, around £200 of which we have used for products to use for this project. We also intend to apply for additional funding from the Strathclyde Union's Societies Fund, which we hope to use for entry fees, and we also plan on our own internal fundraising. We also hope to be able to reuse our motor from a previous year, as that would allow us to cut down on costs significantly as well.
And now moving on to the overall timeline. This shows the key dates for the team, as well as our plans for manufacturing and testing.
So just to wrap up, as we head on towards the critical design review, we'll be finishing the design for the rocket, the CANSAT, as well as Firefly, as well as creating and testing components for the rocket, as well as the Firefly dev board that showed up here. We'll be continuing to write and complete our manufacturing and testing plans, hopefully to have some physical products ready for the critical design review, as well as at the time of recording, there'll be a radio test conducted tomorrow to inform our live stream performance on our 2.4 gigahertz band. And finally, we'll be continuing the Firefly certification process, working towards the critical design review as required by the UKRA. And just to wrap up, a thank you to our sponsors, RS Components, JLC PCB, Altium, the Strathclyde Union, the Strathclyde Alumni Fund, as well as ANSYS and SolidWorks. Thank you for listening. If you have any questions, please send us an email.